The word computer was originally a job description for people tasked with manual counting. Because of that history, we still tend to view these machines primarily as high-speed calculators. Yet, mathematical calculation accounts for less than 20% of the workload in a modern system. This diagram shows the actual function of a computer: data transformation. It takes chaotic, raw inputs, like a list of thousands of unsorted test scores, and restructures them into formatted records, like an organized report card. As the data we needed to manage grew more complex, this simple transformation loop had to expand, scaling into a massive branching network of hardware. Modern computing provides the structural backbone for global logistics, translating millions of isolated facts into the systems used to manage cities and industries. To understand why this hardware reaches such massive sizes, we have to look at how a computer translates the physical world into a language it can process. The environment provides analog data. This continuous physical force changes over time, like a heartbeat or air pressure. A computer cannot process this directly. It requires digital data, separate binary states represented by ones and zeros. Hybrid computers act as the bridge. A hospital monitor, for example, reads the analog rhythm of a heart and converts it into the digital data points a doctor needs for an accurate diagnosis. Once the physical world is translated into rigid binary code, the amount of data a machine can handle is limited only by its physical size. Most of us use microcomputers: laptops, desktops, and palmtops. These are single-user systems with a small physical footprint, designed for personal tasks. However, these personal devices are the small gateways to much larger institutional architectures. When hundreds of people need to access the same data at once, we use mainframes and mini-computers. These systems are built to handle massive organizational loads, such as processing insurance databases, managing corporate payroll, and coordinating national railway reservations. Institutional problems require a physical architecture large enough to bear the processing load. At the extreme end of this scale are supercomputers. These massive machines are built for the most complex calculations humanity performs, including nuclear research and long-range climate modeling. Supercomputers are geopolitical assets. In the 1980s, a U.S. technology embargo blocked India from purchasing a Cray supercomputer, stalling several national research projects. Indian scientists responded by forming CDAC, an organization dedicated to building a high-performance machine using only indigenous resources. They succeeded with the Param. It was a world-class supercomputer that proved India could develop its own high-scale processing hardware. By developing the Param, India secured independent control over the complex simulations required for its national security and scientific research. Today, high-scale computing has integrated into the daily operations of almost every industry. Banking and commerce shifted to digital models, using nodes like the ATM to provide instant access to funds, a concept known as anytime money. In medicine, these machines allow us to map complex DNA structures and use advanced imaging to diagnose diseases deep within the body. This same processing power has enabled the shift toward paperless offices and virtual classrooms that connect teachers and students across different countries. With DNA mapping and instant global banking, we use high-scale processing to analyze the human body and manage resources across continents in real time. Whether predicting a monsoon or moving money through a phone, every modern solution relies on this process of turning raw data into human action. Computing has moved into the background, operating as the essential infrastructure behind every modern logistical and scientific breakthrough.